All right, so thank you very much for the organizer for putting up this wonderful workshop. I'm very happy to see that it's with a lot of participation despite its online feature. And of course, also to thank them for giving me the opportunity to present some very fresh results we have obtained at our Max Planck Institute in Halle regarding this 2D XY ferromagnetism in a true van der Waals monolayer in 2 dimensions. So this work has been recently submitted, so I put in here also beneath the title the reference for your records. And of course, this was result of a great teamwork, and that's why I will start acknowledging the people involved in the project. So in the MPI team, it's people with different expertise that came together, and that's why it's very, very good to see the progress from people from different backgrounds and working together. So especially I want to thank the student Jin Rong Ri, because she was devoted a lot of effort and energy in growing these wonderful samples that we could measure magnetically. So of course, I would like to thank also the wonderful support for the 2 beamlines where we have been doing this magnetic measurements in Barcelona and Alba, our collaborators from the Boreas beamline, Manuel and Pierluigi, and also in Bessie in Berlin, where we had also wonderful support from Florin Radu and his team at the beamline. So the results I'm going to present as have been verified in 2 different beamlines, so that's also worth to mention. And of course, I would also like to thank you very much, my mentor, Stuart Parkin, for this excellent opportunity to start this state-of-the-art research at MPI Halle. And here I put here a picture of our building that is now fully renovated. And not only the building is renovated, but all the labs are in a very good shape now, and I'm happy to present these results that will start from projects from the scratch. So this outline of my talk will be very simple, since I'm going to present only one of the project, which is this observation of this magnetic system with 2DXY magnetism. So I will just briefly introduce the different kind of magnetic model systems that are Ising, XY, and Heisenberg, and also put in the context our work to what has been done already in the past, because there has been a lot of work doing by the surface science community, working on monolayers on surfaces in this regard. So after going to the experimental results and data, I will finalize with a short summary and outlook. So just to refresh your minds for the people who have not been maybe following all the talks in the past days, we have been talking a lot about this Fermi-Magnet theorem that restricts long-range order in 2D systems with continuous symmetry. And now it's a consensus that when you have a symmetry breaking like anisotropies, you can lift this restriction and realize 2D magnetic ordering. And so far in the true monolayer regime, there are only so far 3 examples that have demonstrated that. That's chromium iodide, chromium bromide, chromium triiodide, tribromide, and FGT. And those materials have a very strong out-of-plane anisotropy that makes that possible. So it's worth to mention that for chromium iodide and FGT, the magnetic assessment was done by Moog tunneling devices, and for chromium tribromide was spin polarized STM. So yeah, I will in addition to this main or the first material that were discovered actually back in 2017. There are a few other examples of that are also worth to mention. We will hear maybe later today also the example of this vanadium 5 selenium 8, because this is also an interesting example of a film that loses magnetism in the monolayer regime, similar to what happens in chromium germanium telluride. When you go from the bilayer to the monolayer, you don't have a magnetic order anymore, presumably because of this weak anisotropy and this Heisenberg character of the system. There's another interesting recent example. This is chromium-2 tellurium-3, where they have a very peculiar observation that when you reduce the thickness, they don't get it to the monolayer regime, but they reduce the thickness up to, you can see here, 5 or less than actually 10 nanometers, and the TC increases dramatically. So that's actually another, although this is not a true 2D regime, that might give us some hints of other type of interaction that are important in this regard. But okay, the main point here is that you need, so far this magnetic ordering was achieved by a sizable out-of-plane anisotropy. So, but how about these in-plane magnetic systems? Is it possible to achieve also this long range ordering with in-plane magnetized systems? So that's what my talk would be about, basically. So, as I mentioned before, there has been a lot of studies on low-dimensional magnetism, mostly on monolayers on surfaces and also on bulk materials, layer bulk materials. So the very general classification, depending on the spin dimensionality of the system, is the Ising, the XY, and the Heisenberg class. And as you see here, it depends strictly on the spin dimensionality. That means in the Ising, you have only one direction in this, that the spin can be stable. In the XY, you have a planar system, and Heisenberg, you have an isotropic case. There are also some special cases of what people call anisotropic Heisenberg. It is basically when you have probably a lot of either too weak or competing anisotropies that allow also for this the spin to be allowed to point in the 3 dimensions. So yes, and for the people working in surface science already 20 years ago, there has been a lot of examples of Ising, XY, and Heisenberg type systems. Mainly, as I said, deposited by ultra-high vacuums, metallic atoms, magnetic metallic atoms on very crystalline substrates. And one thing that I would like to mention here is that for the Ising case, of course, you need a strong uniaxial magnetic anisotropy. And usually in this 2D materials community, it has been also said that the Ising type must be an anisotropy out of plane. That is not strictly correct, because an Ising type can be also an in-plane magnetized system with a strong uniaxial anisotropy, for example, given by magnetocrystalline anisotropy. So here you will find also 2 examples of this kind. So for the XY, of course, you have an easy plane anisotropy. That means the spins prefer to lie in a plane compared to any other directions. And there has been also some examples, at least much fewer examples than for a uniaxial case, simply because easy plane systems are much harder to get when you have a very crystalline and, a very strong crystal field. And you can find here all this in a very nice report. I'm giving here the reference. There's a huge list of materials that have been studied so far with in situ methods. So there's a second difference, or second, let's say, second manner how you can distinguish these 3 different magnetic classes, not only by measuring the anisotropy, but also looking at the details of the phase transition. For example, at the phase transition, you will have order parameters such as magnetization or susceptibility that will decay with a power law. And this power law is related to critical exponents. And these critical exponents, I highlighted here in the red box, are specific for Ising and XY systems. So for Heisenberg, it has not been developed because it's usually the isotropic case has no magnetic orders and thus no ferromagnetic to paramagnetic phase transition. So that's why it's very important to assess which type of magnetic system you're dealing with, not only to measure the anisotropy, but also to have a close look at the phase transition and see how, and measure one of the order parameters, magnetization and susceptibility. It's worth to mention that there are more than this order parameters, but for the sake of simplicity, I just mentioned that one that are going to be relevant for this talk. Okay, so going back to our to our 2D materials and the ones that have been discussed here. So to point it in the context, the icing class will belong the chromium triiodide and bromide and FGT, and the Heisenberg, or let's say we still don't know if it's anisotropic or not, CGT and this vanadium biselenide. However, for the easy plane anisotropy, it is still a missing building block, and that's what we want to find out today. So basically, okay, there's another also important thing here, and there are many theoretical works that that say that both chromium iodide and chromium bromide are not fully icing systems. That means that you will have probably other type of interactions that compete with this uniaxial anisotropy alpha plane. But this is just to give you some information that this is just a broad classification, but inside all this type of magnetic models, there are also very fine details about it. So just we're going to focus on this 2D XY system. This is a system with easy plane. What you see here, it's the spins can rotate in one plane, but are confined to this plane. So there, as I told you before, there were two approaches to get this quasi 2D XY behavior by growing monolayers on surface. The issue here, I say quasi 2D XY because there are some perturbations to the model that preclude to get this to this fully 2D XY regime. So for the case of monolayers on surfaces, we have an issue, which is the strong crystalline-induced in-plane anisotropy. So it's of course obvious to think that you have a very strong crystalline system as a substrate. The monolayer will order according to that, and that would be like detrimental for the XY system because then you will have a preferential orientation given by the crystal. And more complicated than that, this in-plane anisotropy is highly dependent on the crystalline field strength and also on the symmetry. If you have an hexagonal or a cubic or a tetragonal substrate, you will have different symmetries and also crystalline field strengths. In the case of layer bulk materials, that's we know it's the easy case even now, that when you don't go to the true monolayer limit, you will have always an interlayer and finite interlayer exchange that precludes to treat it as a fully two-dimensional XY system. So I want to get a bit more detail to the case for monolayers of surfaces, how the people in theory were treated the crystalline fields as perturbations to the ideal XY model. So when you assume a twofold symmetry that is called XY-H2, for strong crystalline fields, you will get to the icing limit. That's actually very obvious because then it's a limit of strong uniaxial anisotropy, and you will destroy completely the XY regime and you will enter the icing regime. In the case of fourfold symmetry, which is a cubic system, it's highly dependent on the strength of the crystalline field, and this can oscillate between icing and XY. And this is there's also, I want to point out, there's a very nice review by Andrea Taroni while he was still doing research. He studied this or made a compendium of these materials and found out that depending on the crystal field, the critical exponents will oscillate between the icing and the XY regime. And he treated it mostly for the fourfold axis type because this is more ubiquitous system in case of crystalline substrate used for monolayer growth. And last but not least, we have the XY-H6, which would be an hexagonal crystal field. And this, according to theory, is the less perturbative for the XY model. So in summary for this introduction, the roots to get an ideal 2D XY model system would be a minimal substrate interaction. That means a decoupling from your crystalline substrate. Of course, no interlayer exchange. That means that you have to assess that you are really in the 2D limit. And of course, you will have, if you have a crystalline material as such, you will prefer a sixfold crystal symmetry in the plane to have a less possible perturbation to the XY model. And that's how we came to that, to the study, to the motivation. That would be all these three conditions will be fulfilled if we can prepare an hexagonal monolayer on a van der Waals substrate. And in that case, we went for chromium chloride. This is an in-plane layer anti-ferromagnet in the bulk. So I think there has been already talks about these three highlights before, so I'll be very short in explaining just to pick up the relevant points for this material. So it is a layer antiferromagnet with spins pointed in the plane, and the intralayer coupling, so within a layer, is mediated by superexchange via the chlorine ligands. The bulk TC is 17 Kelvin. So, and there was also, of course, well studied in the bulk. This is the phase diagram. So in the antiferromagnetic bulk, you require relatively low critical fields to break the antiferromagnetic phase. So you can find this data in this reference. So you see that the spins are in the plane, but when you apply a perpendicular magnetic field, after a critical value, the spins will follow in the direction of the field. The question is for us, what will happen if we go to the monolayer limit? First of all, if it will retain its intralayer exchange and in-plane EC axis, because removing the intralayer exchange is not as easy as just removing the interlayer exchange and hoping that everything will work as such. So it is the property is a bulk property. So that's for us was an open question, and also if it will order magnetically at all. So far, we have been also looking at literature, but all the exfoliation experiments failed so far in prepare a true monolayer chromium chloride, presumably to the degradation issues in the monolayer regime, probably that are more critical to chromium iodide, because in chromium iodide is possible. So there were no reports of any tunnel device experiments whatsoever. So we decided to start the MPI growth of this material. So how I'm doing with time, if I may ask the chairman?
You still have 10 minutes.
10 minutes, okay.
12 minutes.
12 minutes, okay, great. Mm-hmm. So then, just briefly to mention how we prepare the samples. We have two MPIs attached to within an in situ cluster. That is, of course, with an STM and other surface tying techniques. Very important here is that once we prepare the sample, it never sees air. So it's everything ultra high vacuum for all the characterization that I'm going to present in this talk. So the growth, we prepared bilayer graphene from silicon carbide. So we check the quality and the coverage with STM before preparing the chromium chloride layer. And we do it in our MPI. And when you see with by read pictures that you see here the substrate diffraction pattern, you will have signals from silicon carbide and graphene. And once you put one monolayer of chromium chloride, you see immediately the diffraction related to the film. So, and that's one important thing to mention here. The film is nicely 0111 oriented. That's how we would expect it. But inside the plane, it has an in-plane twisting of domains. So that means that when we see along one high symmetry direction, we can see the lattice parameters of the hexagonal for both center to edge and center to side hexagonal lattice parameters. So that means that we don't have a purely single crystalline orientation inside the plane. That will be very important for the interpretation of the magnetic properties. So then we, of course, we want to assess with STM that we have indeed full monolayer coverage. So actually with the read, you already see when you see the disappearance of substrate and substrate lines, you will also think that it's a full monolayer coverage. Nevertheless, we went to the STM, and as you can see here in this topography image, this monolayer is like a carpet, and it deposits on all the terraces morphology that is given by the silicon substrate, silicon carbide substrate. But most interestingly, when we go inside one terrace, we can see a very beautiful moire pattern. And this moire pattern is the interference of this chromium chloride and graphene layers. So the existence of moire patterns give us the hint that our structural properties of the chromium chloride layer on top are very, very, very nice. And here we can also see that when we go different parts of the sample, we can see a different pattern, different moire pattern. And that underlines the fact that we have not always the same orientation of the domains in a very large scale. So that's consistent with Reed. So then we transfer our sample with our ultra-high vacuum mobile suitcase to the low temperature STM. And here we can see that at very low temperature, we can nicely, by scanning tunneling spectroscopy, we can infer a band gap of 1.6 eV. And most importantly here is that we have close to the intrinsic band gap and no defect state whatsoever in our film. And when we went to the beamline, of course, we want to see the chemical integrity of the surface before starting the magnetic measurement. And here we see the oxygen KH is completely absent, and we have only the chromium absorption H. That's actually very good news, because that means that there is not even any impurity on the surface. So we are probing really the pristine monolayer chromium chloride. So just very briefly, for the people that are not familiar with XMCD, that's a technique we use to probe the magnetization of the magnetic properties of the system. It relies on the transition from core levels of a solid to the to states that are close to the Fermi energy. In the case of D band metals, you will have a specific absorption cross section from circularly polarized light, depending on the spin, the orientation of your bands. If it's spin up or spin down, and this contrast, it's called the XMCD signal. And so that's why you have to do for light and less circularly polarized light, and difference would be proportional to the magnetization. The advantage compared to magnetic optical Kerr effect, called MOG, is that here you have the possibility to study the magnetism element specific. That means you can, for example, investigate what is the local magnetic moment on chromium on chlorine separately. So that's also very important for the magnetic characterization of those monolayer materials. So going to the results. So we have here the XMCD spectra taking at 2 Kelvin at the saturation fields. And we see here at the chromium L edge a very large XMCD signal of around 100%. So that's actually also underlines the quality of our chromium chloride monolayer. And we can even see that we have a sizable XMCD signal at the chlorine line. This is also the LH at low photon energies. So that means that we have, at least when we have a 2 Kelvin at the saturation, that's when we expect that all the spins are saturated, a large magnetic moment. Now the question is, if we have a remanence, because this is a high fields, what happens if we do a field-dependent measurement? And actually that's the key point of the talk, that we were able to see in the low field region an hysteresis loop, an XMCD hysteresis loop, and we see a phase transition between 10 Kelvin and 12.5 Kelvin. And here you see very, very beautifully how the hysteresis loop closes when you increase the temperature. And that hints us that indeed we have long-range magnetic ordering in this sample. So then, of course, very important is the anisotropy. The anisotropy we try to measure with grazing and normal incidence to see how it behaves when we have the sample in or out of plane. And you see that the sample, the EC axis is clearly in plane, as you see from here on the right-hand side. And the anisotropy fields are relatively large compared to what we were expecting. That was between 0.5 and 0.9 Tesla. So the theory, maybe I will skip this, just give you the reference, that says that some papers said that the EC axis would be even C instead of in plane. So the anisotropy in the pristine chromium chloride treated by theory was so weak that even some people will say, oh, I'm not sure if it's in or out of plane. But in our case, it's very clear in plane anisotropy with sizable anisotropy fields. So to understand these anisotropy fields, it's good to look at the anisotropy energy that's composed by three terms: the single ion dipolar magnetic exchange term, following here one recent paper that argued that this component would be also important to explain the anisotropy of this tri-highlights. I just very briefly tell you what are the important parameters here. This is the spin-orbit coupling strength. This is the orbital moment anisotropy. For the dipolar term, we have everything, and it's everything relatively simple. But here, there's also the degree of triangular distortion that will come into play. So for our system, this degree of covalency, which is also the bandgap we extract from STS measurements, the spin-orbit coupling strength can be, taken from literature values from chromium and chlorine. And what is important for us is to determine why is our anisotropy so high, and there could be any orbital moment or trigonal distortion in our MPI ground samples. That will explain actually this large anisotropy in the plane. So basically, we have here the XMCD measurements for normal and grazing incidence, and you know that you can do this XMCD sum rules to extract the spin and the orbital magnetic moment. And to cut the long story short, we have here observed a spin magnetic moment which is close to the 3 μ expected for chromium 3+, but we have here a very it's appreciable orbital magnetic moment, and most importantly, we see a difference in magnetic moment when we put the field in plane and out of plane. That means that we have a small but indeed measurable orbital anisotropy in favor of the in-plane easy axis. The second point was the trigonal distortion. So trigonal distortion is difficult to measure usually, but in this PRL paper, they treat it as the angle. This is the bond plane in which chromium and chlorine are bonded, and this is lying at 30.35 degrees in the theoretically relaxed structure. So if you do angular dependent measurements, in our case, we are able to see an offset of this bond plane with respect to the angle. And this large trigonal distortion, we believe, could be, we have to do a bit more studies, what would this trigonal distortion represent in terms of strain or real atomic bond lengths. But it's indeed one question, or let's say one factor that indeed underlines the high values that we're having in this anisotropy of this chromium trichloride. So the main message here is that we believe that this anisotropy is coming from this trigonal distortion in our MPI ground samples that leads also to this orbital magnetic moment anisotropy. And when we do roughly they put the maths here, we arrive to 1.1 Tesla, which is not so far away to the values that we have observed experimentally. So I think I'm running out of time. Just to give you some idea of what we have done, as I told you, also we have looked at the phase transition, and when we model this temperature-dependent magnetization, our fittings were rather fitting with a 2DXY model rather to the icing. We did this. This is a remanence value. We took it from this hysteresis loops, and the extracted TC that we got is 10.7 if you consider a 2DXY model. And last but not least, what we did is also an AROT analysis. For that, you don't rely on the low field region of the magnetization, but you rely on the high field region of the magnetization of the MH curves. And you are, with some of the scaling laws, you are always able to get this kind of critical exponents for magnetization and susceptibility. And in our case, maybe I leave just for the questions. And people will ask how you determine that this fitting is it's consistent. There are many criteria that I could maybe leave it for the questions. I also have try to model it with other 2D models and 3D models, and none of them fit to this critical scaling analysis. So that we are pretty confident that the 2DXY model is the one that we are having in our system. Of course, this is also the existence of this 2DXY is related to the BKT, this Berezinski-Kosteles-Stodel transition, which is a quasi-long-range order formed by vortex-anti-vortex pairs. So this is, of course, very important also for us to explore it very close to the phase transition if we can have some observation of this vortex-type pair close to TC. And there has been also some predictions of merons in chromium chloride. If this is related to BKT, we still don't know, but there's definitely some topological spin textures that also happen in the 2DXY systems. And to summarize, I will leave you with this slide. What are the implications of this 2DXY magnetism in monolayer chromium chloride? I think we have opened up an exciting route to explore in-plane.
The Bohr spinalis, but it doesn't work there.
Okay, it's okay. I don't see.
Sorry?
It's fucking...
Okay, so...
Sorry, I don't know.
I don't know either.
But it can be done by phone. Sorry.
Okay, just to conclude, the implication of this 2DXY magnetism of monolayer chromium chloride is that we can integrate this now an in-plane magnet in van der Waals heterostructures. Of course, from the fundamental side, we can explore the BKT physics in truly 2D magnetic systems. That's a thing that is fully underexplored. And also it may give rise to observation of topological spin textures, which are the merons, which are a kind of family of Skirmans. And the key factor for us to achieve this 2DXY magnetism in chromium chloride is its quasi-freestanding nature. That I explained at the beginning that is with the van der Waals interaction with the substrate, even though it's with MPI, we have this van der Waals interaction, so we don't have any perturbation from crystalline fields, and we have a hexagonal symmetry inside the film with twisted domains that also helps to stabilize this kind of 2DXY system. And with this, I would like once again to thank my collaborators and thank you for the attention.